Have you ever really stopped to think about how you're seeing the world right now? I mean, how does all the light bouncing around you turn into this perfect 3D movie that's playing inside your head? It happens so fast, we just take it for granted. Well, today, we're going to pull back the curtain on the incredible physics of sight. Let's dive in. So, let me start with a question for you. What do you think is the single most advanced, most powerful camera you will ever own? No, it's not the newest smartphone. It's not some crazy expensive professional camera. You got it. The answer is literally right in front of you. Your eyes are an absolute marvel of biological engineering, and they can pull off feats that our best tech can only dream of. So let's break down exactly how they do it. Thinking of your eye as a camera is actually the perfect way to start. I mean, they both use a lens to focus light, right? But here's where your eye just leaves the most expensive camera in the dust. Its unbelievable ability to shift focus in an instant. A camera has to physically move its lens back and forth. Your eye, it just flexes a muscle. Okay, so let's get our bearings. This right here, this is our roadmap. We are going to follow a single ray of light on its amazing journey from the outside world all the way through this incredibly complex system and into your brain. So our journey begins right now. Just imagine a tiny particle of light, a photon, that's just bounced off, say, a tree in front of you. It's zipping along at the speed of light, and it's headed straight for your eye. So what's the very first thing it hits? That first stop is the cornea. It's that clear, dome-shaped outer layer of your eye. Now, you might just think of it as a protective window, but it is a seriously powerful lens. In fact, it does about 2/3 of the heavy lifting when it comes to focusing light, all before it even gets to the main lens inside. Okay, so after passing through the cornea, that ray of light heads for the pupil. Now, the pupil is just the opening, but the real star of the show here is the iris. That's the colored part of your eye. The iris acts just like the aperture on a camera. It shrinks the pupil in bright light to let less light in, and it opens it up wide in the dark to let more in. It's a completely automatic light control system. Pretty cool, huh? Once it's through the pupil and the main lens, the light finally hits its target at the very back of the eye, the retina. You can think of the retina as the film in an old-school camera, or the sensor in a digital one. It's this light-sensitive screen where the image gets projected. And here is a wild little fact for you. The image that forms on your retina is actually upside down. But seeing doesn't just stop at the retina. When that upside-down image hits it, millions of tiny, light-sensitive cells, called rods and cones, fire up. They instantly convert that light into electrical signals, which then get whisked away to your brain through the optic nerve. And it's your brain that performs the final magic trick. It takes all those signals, processes them, and flips the image right side up, so we see the world the way it's supposed to be. So we've traced the path of light, but what about focus? How can your eye look at a book in your hands one second, and then a distant mountain the next, and keep everything perfectly sharp? This is where your eye really shows off. This biological superpower has a name. It's called accommodation. It's the eye's absolutely incredible ability to change the shape of its own lens, adjusting its focal length on the fly. It is a constant, subconscious process that keeps your world in crystal clear focus, whether you're staring at something an inch from your face or gazing at the stars. So how does this actually work? Well, let's say you're looking at your phone. Tiny muscles that are all around your lens, they contract. This lets the lens itself sort of relax and bulge out, becoming thicker and rounder. That new, thicker shape has the perfect focal length to bring that close-up image into sharp focus on your retina. And now, look up at something far away. The exact opposite happens. Those same little muscles relax. This pulls on the lens, making it thinner and flatter. And a thinner lens, well, that's perfect for focusing on things in the distance. It is this constant, seamless dance between muscle and lens that gives us our clear, dynamic vision. It's just amazing. Of course, this delicate system doesn't always work perfectly. And when it doesn't, that leads to some very common conditions that I'm sure many of us are familiar with. Times when the world just looks a little fuzzy. The two big ones are myopia, which we know as short-sightedness, and hypermetropia, or long-sightedness. With myopia, or short-sightedness, the image focuses in front of the retina, which makes things far away look blurry. With hypermetropia, it's the opposite. The image wants to focus behind the retina, blurring things up close. Thankfully, we've got a pretty elegant fix for both. So how do we fix it? with corrective lenses. For short-sightedness, we use a concave lens. It spreads the light rays out just a tiny bit, so your eye's natural lens can then focus them perfectly onto the retina. And for long-sightedness, we use a convex lens. This one gives the light an extra focusing boost before it even enters your eye. It's just simple physics, but what a brilliant solution. So we've spent all this time talking about how our eyes bend and focus light to create images. But it turns out this exact same principle, the bending of light, is also responsible for one of the most beautiful sights in all of nature. Yep, let's talk about rainbows. I'm sure you've seen this before, right? You shine a beam of what looks like white sunlight through a glass prism, and out the other side comes a beautiful spectrum of colors. This right here is the fundamental key to understanding how a rainbow works. Now, there's a scientific name for this, and it's called dispersion. It happens because each color of light is actually a slightly different wavelength. And as light passes through a medium like glass or water, each of those wavelengths gets bent at a slightly different angle. Violet light bends the most, and red light bends the least. So where are the giant prisms in the sky that create rainbows? Well, right after it rains, they're everywhere. Every single tiny suspended raindrop floating in the air acts as a perfect little prism, just waiting to catch the sunlight and split it apart. So inside each and every one of those raindrops, this beautiful three-step dance is happening. Sunlight enters the drop and bends. Then it bounces off the back surface of the drop. And finally, it bends again as it exits, spreading all those colors out for us to see. A rainbow is nothing more than the collective result of this happening in millions and millions of raindrops all at once. And this all brings us to one final, kind of mind-bending thought. We've established that what we call color is really just our brain's interpretation of different wavelengths of light hitting our retina. So here's the question. If a tree falls in the forest and no one is around to hear it, does it make a sound? Well, what if a rainbow forms in the sky and no one is around to see it? Does it even have color? Something to think about. Thanks so much for joining me.